All right, so those who've been with this lecture series from the beginning, I don't know if there are many of you out there, but if so, you remember that I decided to sort of focus on this catalog of spacetimes, and it's been a heck of a long time since I've gotten back to it. The idea being that, we should understand everything in this catalog. If you understand general relativity, everything in this catalog should make some kind of sense. Now, it's pretty ambitious, actually, right? Because there's some pretty esoteric stuff in the catalog. Let me give you an example. We're going to study the Schwarzschild spacetime, right? We're going to derive the Schwarzschild spacetime. Now, in the catalog, and we've kind of looked at some of these things before, a lot of this stuff should make perfect sense to everybody right now. For example, this is this represents the line element, right, which is all based on the metric. The metric is a metric tensor, a 0-2 rank tensor. Deriving this should be not an issue, right? The idea of taking this and switching coordinate systems and coming up with new metrics, that also should be trivial. In the catalog, it's kind of interesting. They don't literally write out. They don't write out G00 equals, G11 equals. They're expecting you to look at this thing and realize, oh, G00 equals minus 1 minus RS over RC squared, right? So clearly they're not using G equals C equals 1. And I think that's good for the catalog, right? The catalog, it's assuming that you're smart enough to figure all this out. You know G equals C equals 1, but it's kind of a pain in the butt to go from G equals C equals 1 units and then turn it into other units. It's much easier to do that if you actually carry the C squares around in the whole system, right? So they do define, they do use these other units there. And I think that's a good idea for something like the catalog. It's not a good idea for sort of the pedagogy of learning about all these things, right? Because units is not what we're worried about when we study the nature of differential geometry and the nature of the Einstein equation. We don't want to get bogged down in units because we're not like calculating a real neutron star. We're trying to figure out what this theory means. But the guys who are out there using this catalog all the time, it's convenient. So, I want to be really arrogant and say, oh, they get a pass for using units other than G equals C equals 1. But here it actually makes total sense to do that. Anyway, so we should all be understanding what that is. And the first thing that they decide to list are the Christoffel symbols, right? That's the first thing, right? Given this metric, these are the Christoffel symbols, right? And the Christoffel symbols are the core of what is geometry on a manifold. And you could choose any Christoffel symbol for a manifold you want. It's essentially an arbitrary process. But if you have a metric defined on the manifold, there is one set of, let me get the language correct. You could choose an arbitrary connection on a manifold, right? The connection can be arbitrary. But if you have a metric, the metric connection is not arbitrary. And the metric connection is defined by things we call Christoffel symbols. So in principle, the Christoffel symbols themselves are not arbitrary because the definition of a Christoffel symbol is almost always the connection defined by the metric. So the metric becomes the foundation. If you see the word Christoffel out there, you know you're not dealing with some abstract manifold that has a arbitrary connection defined on it. You actually are dealing with a manifold that has a 0-2 rank tensor, metric tensor field, and that metric tensor field is being used to create a connection. That connection is called the metric connection or the Levi-Civita connection, and that thing is defined with Christoffel symbols. But we all know that now, so we know how that works. But notice how important it is. It's the most important thing. And then you see we've got these partial derivatives of the Christoffel symbols. Well, why is that the most important thing? Why is that important? Why is it so important that it's listed in the catalog? And the fact is if you want to calculate the Riemann tensor, right, you need these derivatives. So they say, hey, this is a catalog. Let's make it easy. So they put it in there. We'll be doing that in this lesson today. We'll be using this. Well, actually, what we'll be doing in this lesson today is we're going to be deriving this, right? This is the answer to the problem that we are going to solve today, right? So, wow, big foreshadowing. It's kind of like I'm allowed to spoil a movie that was made 10 years ago, right? In this case, I'm spoiling a calculation that was done probably not quite 100 years ago, right? Probably not quite 100 years ago. Let me find out. When was the Schwarzschild space-time discovered? Hold on. Holy crap. The answer is, wow, 1915. You know what? I remember this story. Wasn't this a story about some guy discovered it in the middle of World War One? Yeah, well, 1915 was in the middle of World War One. I don't know if this was on the front line. I better find out, or people are going to say in the comments. Yeah, damn, he is the guy. So he discovered this while fighting in the German army in World War One, and then he dies the next year. I guess he died in 1916 of some horrible disease he caught. Some horrible disease while fighting on the Russian front. Oh my goodness. Well, hats off to you, Carl. His name was Carl with a K. Carl Schwarzschild. Anyway, that's sad. So he discovered this solution, and it's not a spoiler to show the answer, but we are trying to reproduce his logic. Today we're going to be reproducing the logic of some poor guy who was stuck on the in the German army during World War One, in one of the most miserable points of human history. This man is thinking about one of the greatest intellectual accomplishments of human history, the general theory of relativity. And I don't think that's an exaggeration to say. I say if you had to rank the singular most fantastic accomplishments in human history, the discovery of this theory is by no means a logical path. It was not something that was supposed to happen at that time, or it could have happened. If we were just discovering this theory today in 2020, right, nobody would say, wow, this should have been discovered so much earlier, right? Nobody would necessarily be saying that. It's not like there was something in the air in 1920 that made all of this logical. The special theory of relativity, maybe you could argue that all the building blocks were there and somebody just had to dive in and say, maybe the implications of electromagnetic field equations being invariant under a Lorentz transformation, maybe if we took those implications to their full serious limit, maybe there's something there, right? That was a big insight. It was a big commitment. It was a big step to take, an intellectual commitment. It's like, hey, let's dump Newton and just see what happens. And wow, you know what happens? Not much. It's Newtonian physics doesn't change for almost every circumstance we've ever seen, but clearly, let's put it this way: the implications of Lorentz invariance electrodynamics, those implications were nothing that would influence the experimental observations immediately at the time. So it was still an open question whether taking that commitment really ruined physics, and in fact it didn't. It did the opposite. I'm not so sure that the same was true for this. In my opinion, this is just a piece of intellectual discovery that drops into human history. Kind of like the moon, the Apollo mission, right? The Apollo mission to the moon in the 1960s doesn't seem like it really belongs in that era. It's something that we should be doing now, but they did it back then. And in fact, all right, anyway, I'm beginning to digress. But the point is we're going to reproduce this exercise. So the partial derivatives, we're going to need those things, right? The Riemann tensor, right? This is the granddaddy of the curvature tensors, but it's built on the components these components. So they give you the components first, and they say, hey, don't worry, we'll calculate these guys for you. If it's not on this list, it's zero, right? So there's a lot of zeros in this Riemann tensor, so that's kind of interesting. This idea of the local tetrad, we actually talked a lot about this, right? We talked about creating a local tetrad when we did some of our analysis. We didn't really dive into the full story there, but but you should have some familiarity of what this is. This is an orthogonal basis. You know, it's the orthogonal basis at every point in the tangent space. It's constructed by some constant times a coordinate basis vector. So if I take the coordinate basis vector in the tangent space and multiply by this constant, I create vectors that are all members of the tangent space. Every one of those guys is a member of the tangent space at the point P. This guy, this guy, this guy, and this guy. They're totally legitimate vectors. And but the beauty is that they're orthogonal, right? They're orthonormal to one another, which is good. And it's something, I don't think we're going to go into much detail. I don't think I'm going to worry about that topic for the rest of these classes. But the point is you can then do curvature using these guys. You can create a curvature tensor in that basis, right? I think they do it eventually. Yeah, the Riemann tensor with respect to the local tetrad. Here it is. Notice how simple it is, right? With respect to the local tetrad, there's fewer components. It's kind of interesting. And then you can also do the same thing with the Newman-Penrose tetrad, which is now based on the local tetrad. So you've gone from the coordinate basis to the local tetrad basis to the Neumann-Penrose tetrad, right, where you start combining the local basis to get this thing. Notice you get a complex number here. That's really, really important. You end up with these things called spin coefficients. Those are more advanced topics we're not going to get into. But the point is the catalog of spacetime is where it's at, and the goal for today is to derive this bad boy right here. We're going to reproduce Mr. Schwarzschild's work. Okay, so with that introduction, let's begin. So the question we're after is, can we create a spherically symmetric spacetime? Can we mathematically describe completely a spherically symmetric spacetime? So let's just look at what this statement is telling us to do. First thing we're looking for is a spacetime. So implicit with the meaning of spacetime is we're looking for a four-dimensional manifold, right? A four-dimensional manifold, and that four-dimensional manifold will have a metric, and the metric of that four-dimensional manifold, right, G mu nu, that metric exists on the four-dimensional manifold. The metric itself, so this is the points on the manifold is x, right? And then this gives you a metric tensor at each point x. The point, and this is a 0-2 ranked tensor, obviously. The point of this is that this is what a spacetime is, right? That is what a spacetime is. It is a four-dimensional manifold with a metric, with one additional fact. Can you see what the additional point is, right? It's not just an arbitrary metric. It can't be an arbitrary metric. It has to be a metric with signature, I guess in our work, the signature of G is equal to 2, right? Which means that the metric can always be at any point diagonalized to -1, 0, 0, 1. I'm sorry, Jesus. Not that. Not -1, 1, 1, 1, 0, 0, like that. Right? And you can always get the metric at any given point into this form. Right? It's a Lorentzian spacetime. But that's what we mean by spacetime, right? You could speculate on spacetimes that don't have this structure, and that's fine, but you would have to say something special, like we're going to use an oddball spacetime. You know, you could say, okay, a spacetime is just a manifold that has a metric. But spacetime implies what we understand. We understand space, we understand time, we're putting them together, we're modeling the world around us, and the world around us, that model, part of the assumption is that the metric follows this requirement, right? That it's everywhere locally Lorentzian. So that's the first thing we understand we're doing, is we're building a space-time, and when we're building a space-time, that means, you know, establishing the 4D manifold. Well, that's trivial. That's just a mathematical object, and we just say, okay, 4D manifold, that's our arena. But this guy, this is the one we have to work our butts off to figure out. So that's what we're going to do. And we're going to use the Einstein equation to get there. So then the other piece of this is the spherically symmetric part, right? So spherical symmetry is going to basically take us probably 8/10 of the way to the answer, and we're going to work on the last 2/10. maybe that proportion could even be bigger because these problems are just that hard. But we're looking for a spherically symmetric spacetime, and we've already found one because the flat spacetime, right? The flat spacetime where g mu nu equals eta mu nu, that's spherically symmetric, right? If you set up an origin in that spacetime and you set up a coordinate system that was r, theta, and then phi, just a spherical coordinate system, the whole 9 yards, that would be spherically symmetric, right? That would satisfy our requirement. In other words, the Minkowski metric, which in the catalog would look like g mu nu equals, so this is the element for the Minkowski metric in spherical coordinates, just to be clear. So that means g00 equals -1, grr equals 1, and I guess you have these two for the rest of you have g theta is r squared. That would go right here. I'm blowing up this spherical element here. So g theta would be r squared, and g phi would be r squared sine theta. So this is, and this is pretty simple, right? This is easily to dissemble. You can calculate. This thing does have connection coefficients, and it does have derivatives of connection coefficients. In fact, let's have a quick look at them in the catalog. All right, so here they are. We are looking in the catalog, the Minkowski metric, right, in spherical coordinates, and here it is. This is the thing that I just wrote down, right? Remember, I called this part d omega squared, this whole piece right here. And the Christoffel symbols, you can calculate the Christoffel symbols. Each of these is, we're going to go through this calculation soon, but for our case, but here they are. They're not, just because it's flat space-time doesn't mean that the connection is zero, right? What is zero, though? You'll notice that you've got the Christoffel symbols checked, you got the derivatives of the Christoffel symbols checked, local, but then you immediately have the local tetrad. So what's missing? Well, remember back in the Schwarzschild version, you Christoffel symbols check, partial derivatives check, and then you had the Riemann tensor. There's no Riemann tensor in this case because, of course, it's a flat space-time. It's flat, right? So the Riemann tensor are alpha, beta, gamma, delta, and they put the alpha down here. They like to use this form. Equals 0. Every component equals 0. It doesn't matter what coordinate system you're in. Every single Riemann tensor is going to be 0. Now, if you looked at the Minkowski metric in flat space-time, right? If you looked at the Minkowski space-time not in spherical coordinates but in Cartesian coordinates, right? Right. Then what you would have is this would be, well, this would look like dr would be dx squared plus dy squared plus dz squared, and all of the metric elements would just be a constant. They'd be either -1 or 1 or 0. And in that case, remember, these guys are calculated using the metric and some derivative, right? So all those derivatives would be 0. So these would be gone. Then, of course, these are gone. And this is going to still be 0, right? So this is the tensor quantity. If the whole thing is 0 in one system, the whole thing's going to be 0 in every system. Anyway, the point is that don't make the mistake of thinking Christoffel symbols and partial derivatives and of the symbols will be 0 in every coordinate system in flat space. That's not true. The point is Minkowski coordinates do satisfy the notion of spherical symmetry, right? That means, so we're looking for another solution. We're looking for a solution that is not Minkowski flat space-time. Now, we actually talked about what spherical symmetry means vis-a-vis a space-time metric, right? What does a metric have to look like in order to be spherically symmetric? Not every metric is spherically symmetric, obviously, but every spherically symmetric metric must have a certain characteristic. And we discussed this in great detail in a previous lesson. specifically lesson 38. So go back to lesson 38 to understand why a spherically symmetric metric is this. This represents the line element for a spherically symmetric metric. Here is the time coefficient, the radial coefficient, the theta coefficient, and the phi coefficient. So this guy is G00, this guy is G11, this guy is G22, and this guy is G33. The metric is diagonal, and the off-diagonal terms, all zero. Obviously, it's symmetric. Now, the point from that lesson was this is a function of just the radial distance, which I'm calling rho. I shouldn't say distance. It's the radial coordinate, right? Distance is what this gives you, right? Saying the radial distance basically means calculating ds. Well, I guess it would be calculating ds equals the integral of if you were just traveling down the radius, b rho t d rho, right? That would be the distance. Well, it's not even ds. It's now L, right? From rho 0 to rho 1, right? That's the distance you would calculate moving along the radius. So I got to be careful. I don't want to slip the tongue. Radial distance is not what rho is. Rho is the radial coordinate, right? Now, what's interesting, so the way, and just as a reminder, like in case you don't want to go back and review all that stuff, you could just start this lesson, by the way, just believing that any spherically symmetric metric has to have this form. Except that literally what I just said is not true. There are other forms of a spherically symmetric metric that are acceptable. However, those are all essentially equivalent to this form through a coordinate transformation, or this form is equivalent to one of those other forms through a coordinate transformation. The reason we choose this form is because when we lay out our space-time, if this is the center of the coordinate system, so it's r equals 0, if I have a point in space-time whose radial coordinate is rho, say rho 0, right? I can take all the points in the space-time that have a radial coordinate of rho 0. So that's so they have a coordinate of rho 0, but every possible theta and every possible phi, right? And we just do it at one time slice. So let's just say it's at t0, right? So we're looking at just a purely spatial sphere. So everybody has the same t, right? And everybody has the same rho, but we go through all of this. So that's a sphere, just a space-like sphere sitting in space-time at one instant in time, right? The surface area of that sphere, which is something you can calculate using this metric, right? That surface area of that sphere is going to be 4 pi rho 0 squared, right? So we've chosen this metric because what we want is that whatever your rho is, we want the area of the sphere around the center of symmetry to be 4 pi rho squared. We want the spheres to behave like normal. Likewise, what this means is any movement along a sphere, like if I start from one point on the sphere and move to another, the length of that line is going to be exactly what you would expect from a Euclidean sphere whose radius is r0, right? And this form of the metric gives you that. Now, the price we pay is that rho itself does not measure the distance to the center, which we just described a moment ago, right? When we did that integral. Oh, I erased it. But when we did that integral, we calculated that L was equal to the integral from rho 0 to rho 1 of b rho t d rho, right? That integral is clearly not going to end up being rho 1 minus rho 0, right? Because b is this function, this unknown function, or this arbitrary function essentially is this b. So we've given up, in order to have this be true, we give up what radiuses means. Now, we could have gone the other way. We could have insisted that radiuses really, the coordinate point, the coordinate value of the point in space-time at a certain radial distance, that coordinate value reflects the distance from the center of the symmetry of the space-time. But then the spheres would have a different shape. So the choice that we're using for this is that we want the spheres to have the same shape. Okay, now with that in mind, A and B otherwise are arbitrary to make the metric spherically symmetric. This could be any function, and the metric would be spherically symmetric. Now, if you're being a little bit sloppy, you might say, well, geez, problem solved. I'll just pick a function A and B, and we're good. And if you pick the constant function 1 and 1, you would be good, because then you would have a flat space metric. But you could pick any function. I could say, oh, this function is like sine squared rho to the t power, right? I could put that there, and you would still have a spherically symmetric metric. But the point, of course, is not to have just any old spherically symmetric metric. We want the one that nature would choose if the space-time itself was spherically symmetric physically, right? So our space-time has some matter distribution. Well, presumably, like say it has a dot, it has a perfect sphere of dense matter here, and there's like a perfect shell of dense matter around it, and it's filled in with a perfect gas of uniformly dense matter, and these are all spheres, right? These are all cross-sections of spheres around that, and maybe in here there's like a fluid that's of uniform density and temperature and pressure. That's a spherically symmetric distribution of matter, and so there's no reason to think that the metric of this space-time wouldn't be spherically symmetric, right? So in principle, you know, we should be able to calculate this. But our understanding of physics says that whatever this arrangement of matter is, you wrap it up in a stress energy tensor field, and the metric is going to be whatever solves this equation. Whatever metric, whatever G mu nu, which gives us gamma alpha beta delta, which gives us R alpha beta gamma delta, which gives us RAB, which gives us R, and all of those things, right? Which finally gives us G, and we presume that we know this. Presumably, going way down here and figuring out this guy, you want to find that guy that solves this equation. And you can see the mountain you have to climb, right? Because you've got to go through all of these things. And we're actually going to climb that mountain, right? So we're not just looking for the arbitrary spherically symmetric metric. We are looking for the one that solves the Einstein equation and is spherically symmetric and is not flat, right? It's not trivial. It's not flat. So that is our goal. And let's begin. So we've already done a significant part of the setup. We've decided that the most general Schwarzschild metric is going to have these components, A, B, rho squared, and rho squared sine theta. We've chosen rho instead of R because we don't want to confuse this with the radial dimension of Euclidean space, because we're dealing with a different metric. So we're going to name the radial coordinate something different. However, the theta and phi are actually kind of the same as you would expect from regular spherical coordinates, so we'll keep theta and phi. Not too big of a problem. And A and B are unknown functions, but one thing that is known about them that this chart doesn't show is that they're functions of rho. Right? They're not functions of phi, of theta, and they're not functions of phi. They're functions of rho, and they're functions of time. So I could put rho and t. I guess I would have to blow this up and clean it up. But I could put like a rho there and a t there and a rho there and a t there. That'd be fine, right? And because it's a diagonal metric, we know the fully contravariant form. It's just these reciprocals, right? So our solution is pretty far advanced right now. In other words, we've discovered just by spherical symmetry alone that all this stuff is gone. And that's what I meant earlier when I said 9/10 or 8/10 of the work is done. It'd be a really hard problem if the metric didn't have the spherical symmetry and you couldn't make the assumptions we made back in lesson 38 to get to this point. Also, I call it the most general Schwarzschild metric. There's only one Schwarzschild metric, so this is kind of a weird way of saying it. There's only one Schwarzschild metric, and that's the solution that we're after. This is we're going to say this is the general form of a spherically symmetric metric. So I'm going to have to edit that. The most general form of a spherical metric. And even that's not true because, as I said, there's other forms of a spherically symmetric metric that there is a most general form, right? Maybe I should make that clear. I could put a function c here, and I could put a function d here. No. I could put a function c. Well, I guess what I would have to do is I could say, hold on a second. Let's see. How would we do this? First of all, we would erase all this, right? We would say it's rho squared d theta squared plus sine squared theta d phi squared. And then I put a function c of rho and t here, right? Now, all bets are off. Radial distances don't make sense. Areas of spheres, well, radial distances are not intuitive. Radiuses and surface areas of spheres are not intuitive. Nothing's intuitive. So that's probably the most general form. The point is from this most general form, you can do a change of coordinates and eliminate c, or turn c into 1. Basically, you select r in a way that c is always 1, and then b becomes different, and a becomes different, and so we just rename the new a and b back to a and b. So this is not the most general form, but that's the form we're going to use. Because none of these things matter. It's just going to, we have to choose some kind of coordinate system to do our calculation, and we could have chosen any of them, but this is the one we're choosing. I presume it's the one Schwarzschild himself chose. I don't know. I haven't read his original paper. Well, we need physics at this point, right? Our goal is to solve for a and b, right? That's our mission. And the only way to solve for anything is to use the Einstein equation. So now we are at the point where we are using T mu nu. We are using this bad boy. This is finally a thing that we're going to exploit. So the problem is it's too hard, right? We can't exploit it, right? If you have a space-time, we got to say the arrangement of matter is spherically symmetric. So let's do the simplest conceivable spherical symmetry is a compact object of some size, right? I don't know. So this would have some size d, right? Some dimension d. It's a spherically symmetric object, and this would lead us to a spherically symmetric T mu nu. Okay, and in fact, this is how you might study a neutron star. Is you would say, okay, neutron star is very, very dense. So what is the T mu nu of a neutron star? Well, the truth is, I don't think anybody fully knows. We do know a little bit about neutron stars. We know there's some sort of outer crust, right? And I think the outer crust density is definitely different than, an inner crust. Maybe I should change colors. So then there's an inner crust, and it has a different density. And then there's like the core, or maybe the inner crust. And then there's some mysterious, I think the core is like totally unknown. So it's kind of like nuclear matter out here, and then it becomes like mysteriously unknown, maybe quarkish matter in the middle. But, neutron stars come in different sizes, so I suppose there's some whose core is strange, and then there's others whose core is less strange, and I don't know. The point is it's a complicated creature. But when simplified to its most elementary possible level, so we can think about the stress energy tensor of a neutron star, strangely enough, they call it a perfect fluid. A perfect fluid, right? It seems like the most opposite thing you could possibly have to a fluid, right? High density nuclear matter. But a perfect fluid is typically how the people who study such things in great detail like to describe it. And the stress energy tensor of a perfect fluid. So for what it's worth, this is the expression of the stress energy tensor of a perfect fluid. U is the 4 velocity of the fluid itself. So U would be the 4 velocity field of the fluid. So as usual, if we take that to be at rest, then we just get the 4 velocity. That would be 1, 0, 0, 0. And these components would become diagonal, in fact. So the point is, we're not, this is what would land in this situation, this ultimately super simple situation. This is the stress energy tensor you would use. So that means that we now have G mu nu equals T mu nu, or times 8 pi, right? So it seems like, okay, we've set up the Einstein equation, but that's not exactly correct. And this point confused me for a long time. It seems pretty obvious now, and I hope it'll seem obvious to you. But this is a set of differential equations. This statement is true. The Einstein statement is true at that point in space-time and at that point in space-time. And when I say that point, I mean the little one I just drew inside the mass, and then this one that's outside the mass, right? But it's true at every point in space-time. At this point in space-time, G mu nu equals T mu nu times 8 pi, right? And at this point in space-time, G mu nu equals 8 pi T mu nu. And indeed, at this point, and this point, and this point, at each of those 3 points, G mu nu equals 8 pi T mu nu. The point being is, obviously, these guys, they're tensors on the space-time. G mu nu is a function of the space-time. T mu nu is a function on the space-time. And the value of those tensors is different at every one of these points, right? So this expression using this stress energy tensor is only true inside this little piece of matter, right? Inside here, you have G mu nu equals this thing, right? That is true only inside here, right? Outside here, as soon as you break the surface, right? As soon as you break the surface and you're here, all of a sudden, you're in the vacuum. You're in empty space, right? Because our neutron star doesn't have any gases around it. Our neutron star is just like, empty space, empty space, empty space. Ouch, right? Boom, you're on the surface. So right here, this equation is not true, right? Right here, right here, well, let's just put the dot there, right? At this point, what is true? Well, at that point, you're in the vacuum. So T mu nu equals 0, right? Remember, this is a classical theory. We're not worried about the energy contained in the vacuum. General relativity is a classical theory. They don't know about any of that stuff, right? It's a classical theory. So the vacuum has no energy. It is empty. So T mu nu equals 0. So at that point, G mu nu equals 0, right? That is interesting because, boy, that looks a lot simpler than that. And in fact, it is, right? So when we are looking for our spherically symmetric spacetime, we have 2 regions to consider in the simplest possible case. We have the region. First of all, we set up the simplest possible case our imagination can create. And this is like using reverse imagination. Anything more that we're looking for the least possible possible imaginative spherically symmetric spacetime. And that means that we could come up with these spherical shells, right? That's pretty imaginative, right? And it would still be spherical. It would still be a spherically symmetric mass energy distribution. But we're saying, okay, that's pretty imaginative, but I can think of something less imaginative. Take off this last shell. That's one less shell. That's less imaginative by one shell. Well, then take off the next one. Take off the next one. Okay, so all we're left with is this little lump of matter at the center, which is even simpler than a shell, right? So I can't imagine anything less imaginative than that except empty space itself, and we've already kind of said we're not interested in that. So we've gone to the most least imaginative situation, and we found an equation that's still too intimidating. So now we're going to take the next step of making this like totally trivial, and we're only going to look for solutions that are out here, right? So now we are only interested in the places where g mu nu equals 0. The Einstein tensor equals 0. And that is a huge simplification. In fact, so this is a chart. I lifted this chart from my book, the one that's available on Patreon, the book that I'm struggling with and making slow progress on. But the idea here, what this chart was supposed to show, which it fails because it's full of errors, is that the right-hand side of every 10 of these Einstein equations, right? The Einstein equation is 10 equations, one for each, right? I guess I should write it out. G mu nu equals 8 pi t mu nu, right? So this side is all 0, and then this side becomes r mu nu minus 1/2 r g mu nu equals 0. So all these zeros are owing to the fact that we're looking for the exterior solution, right? Where that's exterior to the mass that's at the center of the system. The problem is that g mu nu is diagonal. So this term I shouldn't have included. I got rid of it in these cases, but for some reason I left it in these. So that term is diagonal. So there's only 4 of these guys left that are not 0, 3. Why isn't that one? That should be 0, 2, right? There should be 4 of these, yes. So there's 4 of these guys left that shouldn't be 0. But remember the trace reversed expression where I think we got r equals minus 8 pi t, where r is the scalar curvature and t is the fully contracted energy, stress energy tensor. Remember we did that in the last lesson where we did the trace reversed form of the Einstein equation? Well, if r is equal to some constant times the fully contracted form of t, but t mu nu is 0 in the exterior, then it is certainly true that g, this is t mu nu, g nu mu, which raises mu, turns it to nu, and fully contracts, that's going to be 0 also, right? You put a g over here, you get 0. So r equals 0. So goodness, that means this one's gone, this one's gone, this one's gone, and this one's gone, and they're all gone, right? So in the vacuum, r mu nu equals 0, right? R mu nu equals 0. And when that's the case, we say that the space is Ricci flat, right? It's Ricci flat. That's just a vacuum field solution. So the Einstein equation in a vacuum is always going to kind of look like this, right? It's always going to look like this. It's going to be r mu nu equals 0. And if we actually go back to the catalog of spacetimes and we go to the Schwarzschild stuff, where was that? Here's the Schwarzschild spacetime. We get the Christoffel symbols, we get the partial derivatives, we get the Riemann tensor. It's not as though this spacetime is not curved. It is curved, right? The Riemann tensor is real. It's just that one particular contraction that makes r mu nu. That is 0 everywhere. And he writes, as aspected, the Ricci tensor as well as the Ricci scalar will vanish identically because the Schwarzschild spacetime is a vacuum solution of the field equation. So there he says it right there, right? I think this should have been as expected. I don't know what aspected means. Yeah, writing this stuff is just such a pain because you can't get someone to read it for you because it's a wall of text, right? You've got to practically hire somebody to read it, and that guy's got to know what they're doing. Anyway, so r mu nu equals 0, and they don't even include it here, right? Now, there are other spacetimes where r mu nu is not equal to 0. Let's see if I can pull up an example. So here's one, right, from the catalog. It's called the Ernst spacetime. It's the metric is a statically axially symmetric electrovacuum solution of the Einstein-Maxwell equations with a black hole immersed in a magnetic field. So the stress energy tensor on this side is actually the Maxwell equations, right? So this is there's an electromagnetic thing going on, and there's a black hole involved too. This thing's crazy, right? But here it is. This is the metric of this thing. This guy calculates and solves the Einstein equation. Look at his Christoffel symbols. They're nuts. So each of these has derivatives, right? I didn't even post that. But the point is the Ricci tensor here is not 0. Interesting, the scalar curvature is 0. But the Ricci tensor is not 0. Okay. Now there is something I just took note of over here. You see this lambda in this expression, right? Whenever you see lambda in the Einstein field equations, you kind of tend to think the cosmological constant, because there is a version of the Einstein field equations, which we did not cover, that looks like this, with a minus lambda g mu nu. And what that basically is saying is that no, space-time has some content, right? Because you could put this minus g mu nu over on this side, and it looks like energy content in space-time. So we're treating lambda to be 0 for our work, right? This is subject to some debate, and that's not the point of our lessons, right? We're happy to work with this version of the Einstein equation where the vacuum has no energy content. Now, if we're doing cosmological models, then we need to actually include that. But in this case, what's going on is that lambda doesn't refer to the cosmological constant. It refers to this expression down here. So the electrovacuum solution of the Einstein-Maxwell equations, so what exactly do they mean by that? Well, it's hard to know for sure unless they literally cite the Einstein-Maxwell equation. But generally what the Einstein-Maxwell equation is, well, it's this thing, which I lifted from Wikipedia. So I'm using their literal, the Wikipedia's literal notation here. Well, I changed it. I made it covariant. They have it as contravariant, and I included the full constant that they're using. But the point is here's the G. This is all T, right? This is all T mu nu. Hold on a second. I guess to get this, I need to get this straight, right? This is going to be the only things that survive are alpha and beta. So this has to be alpha and beta, right? Because that contracts, well, what's contracting here? These two are fully contracting, leaving alpha, beta. Here I have psi. This needs to be a mu, right? This needs to be a psi, right? In order for that to work. Okay, now it's all work. Now it's good. So this is the Einstein-Maxwell equation. Notice that they've included the cosmological constant as lambda. I'm not an expert on the Earth space-time, but although we see a lambda here, they redefine lambda in terms of this number b, which is the magnetic field strength. So this is not related to the cosmological constant. It's just a constant. They want you to simplify this expression. So I'm pretty sure that the lambda that typically is associated with the cosmological constant is considered 0 for the version of the Einstein-Maxwell equation that they're using. But regardless, the point is T is not 0, ergo T is not 0, ergo the Ricci tensor of this whole thing is not 0. And that's why, of course, you have a Ricci tensor. Now, it is interesting that it still works out, so you get R equals 0. I'm not going to dig into that, but this is an example where that's not the case. Now, notice, so the vacuum field equations are RAB equals 0, but if you did have a cosmological constant, I guess I shouldn't leave that out. It would be RAB equals, let's see, it would be equal to, I guess it would be not minus, it would be just lambda GAB, right? So that would be the vacuum field equation in a cosmological condition, right? Or a cosmological constant condition, and if lambda was 0, it would be the same anyway, right? But we don't know if lambda is 0 or not, I guess. So if you're doing cosmology and you're studying the vacuum solution, this is kind of what you do. If you're studying a neutron star, this doesn't even matter. It's whatever it is, it's too small to affect the space around a neutron star. So you go with this, and that's what we're doing. And the reason I'm getting into this is because I want you to see what we're doing. Why we're ignoring the cosmological constant is whatever this is, it's not going to be something that affects our little neutron star, and we tend to ignore it anyway, right? So there you have it. So now that's our setup. So I'm going to leave this lesson with the setup that we're using now to march forward. The next lesson is just going to be the mechanics of doing this. But we have to understand why we're doing what we're doing. And the setup is we've got our most general spherical metric, right? I said that this was kind of our most general spherically symmetric metric that and it's not even the most general, right? I qualified all of that. But we've got the spherically symmetric metric that we are choosing to solve. That's this guy. I made the point that A and B are functions of only rho and tau. That's necessary for it to be the most general spherically symmetric metric. Notice how I've left time in there. Many solutions of the Schwarzschild space-time assume from the beginning they make the additional simplifying assumption that it's static. And therefore, they just say A is a function only of rho and B is a function only of rho. We're not going to make that assumption. So I guess I'm being a little more imaginative than the lowest possible state of imagination, which you would also include static. We're not including static in our solution. So these guys could be functions of time in our version of this analysis. And we're only looking at the exterior solution of our brain-dead space-time that has nothing but a piece of dense matter sitting in it. Ergo, we have r mu nu equals 0 because we are not dealing with the cosmological constant. I wasn't planning on talking about that today, but it slipped in anyway. And it's interesting the way it slipped in. I don't know if you guys noticed, but when I talked about the Ernst space-time, the only reason I mentioned the cosmological constant was because they use this symbol lambda here. And lambda is typically what you use for the cosmological constant. Oh, by the way, it's over here too. Obviously, I'm not familiar with the Ernst metric, but this is not the cosmological constant. But because it's the same darn symbol, it reminded me of it. So we went on a bit of a rant. Okay, so next time we start with our setup and we solve for A and B. And once we solve for A and B, that means we have G, and that is the answer.